Hello, everybody. All right, so what we're going to do is we're going to move on into division of polynomials. And one of the stops along the way is going to be we're going to talk about zeros of polynomials. We have a lot to cover, so take your time, go through all this and everything. But it is the last part of graphing analysis that we'll be doing and focusing on. We normally don't do this part until we get to the end because it's after we've gone through all the process and gone through the end behavior and everything else. So that's why we do the zeros of polynomials last. Okay. So let's start with turn points. So a turn point happens in a graph when the graph goes from increasing to decreasing or decreasing to increasing. So that's going to be your turn point. So what that means is that you're going to have a polynomial, a degreed polynomial, and you're going to be looking at it coming from positive infinity or negative infinity. And then what's going to happen, it's going to do some turns, and then it's going to leave to either go to positive infinity or negative infinity. So that's what we're talking about when we're talking about turn points. A polynomial has at most, so this is the max that it could possibly have, at most n minus 1 turn points. So what that means is whatever the degree of your polynomial is, you take that degree, subtract it by 1, and that's how many times it's going to turn in your polynomial. Okay, so if you're trying to remember what the degree is, the degree of the polynomial is whatever the highest exponent is. And just remember, when we normally do these, we normally write the polynomial from the highest exponent all the way down to the constant. So that's what we're looking for. That's what we need to do when we go forward and do these problems. So let's do a couple of practice problems here. We're going to state the maximum turn points of the following. So we've got A, B, and C. So what I want to do sorry, I didn't mean to push that. When I do these, I want to take my highest exponent, whatever it is. So in this case, on the first one, it's going to be a 3. And I'm going to say 3 minus 1, and that's going to give me 2. So if I look at this, and I look at, there it is. And I look at this, and so this is that x cubed minus 5x squared plus 6x. That's what this looks like. And so you notice we have 2 turn points here, and so you notice I have 2 turn points here. So when we are dealing with polynomials, you're going to either come in from positive infinity or negative infinity, one of the two. You're going to do some turns, and then you're going to leave either going positive infinity or negative infinity. So this graph is coming up from negative infinity. We're going to do a turn, go down, do a turn, and then go up and leave to positive infinity. And so that's why we have the 2 right here. On the second one, x to the 13th minus 6x to the 12th minus 27x squared. So we take the 13, we subtract the 1, and we get 12 as an answer. On the last one, x to the 4th, that's the highest exponent. So we get 3 turn points. And so that's what we're going to be looking for. Now, mind you, this number here only tells me my max. It doesn't necessarily tell me that's actually how many I'm going to have. But what I do know is I can't have more than 12. That's it. I'm done. Or more than 2 or more than 3. I can have just 1 turn point, and that's okay. I could have, out of the 12 on this one, for instance, I could have 5 turn points. That's okay. The point being is that you can't have 13 turn points. We can't have 14 turn points. You cannot have any of those. So that's why we do this. So this just tells us our max turn point for this whole entire process. Okay? All right. So actually, let's get into zeros at this point. So zeros of a polynomial. A polynomial can have n distinct zeros. So when I talk about n, when I'm talking about this, I'm talking about the highest exponent. That's how many zeros you could possibly have. Now, what does zeros actually mean? A zero happens when the graph crosses the x-axis. So basically that n, that exponent, tells me I can cross the graph that many times. I can cross the x-axis that many times. If you cannot get the equation factored correctly, so mind you, this is why we have technology, graph the function and just count the zeros. Okay? Again, a polynomial can have n distinct zeros. Doesn't mean that I have to have, like if I have an x to the fifth, I have to have that graph crossing 5 times. No. What this means is I can have no more than 5 zeros. Okay? So just keep that in mind as we go through this process, that when we're going through and we're looking for the zeros or whatever, the highest or the biggest amount that we can have is whatever that exponent is, the highest exponent. So I need you to recall that a polynomial function C is an x-intercept of the graph. So what I'm saying is this, and I'm going to kind of do this a little bit backwards. When we factor things, we wind up with things that look like this: x plus or minus some random number. That random number there, that's your C value. That is where you actually cross the x-axis at. Okay, so that's what this whole entire thing is. They're saying that C is going to be a 0, which means that you can set it up to make it look like this, and then you can solve it. So what you're really doing is you're saying, okay, this is what I'm doing. So I'm saying that this is my 0, which means if I take this C and I move it over here with the X, I'm subtracting it, and I'm having this. Okay, that's what all this is saying. They're saying that when you do that, this becomes a factor for that polynomial. And that's how you turn it into that factor. Okay, you set it equal to x, move that number over, set it equal to 0, and that's now a linear factor. So the majority of these things that we're going to be getting into, you're going to be using the techniques that we did when we did quadratics, pulling out something they have in common, factoring the quadratics. You're going to be factoring by grouping. Those things you can actually apply to be able to use here. So we're going to state the number of possible zeros. So let's start with stating the number possible of zeros. So all we're going to do is we're going to look here at the at each one of these, and we're just going to state how many possible zeros we can actually have. So if I look at this first one here, my highest exponent is a 3, so my max zeros is going to be a 3. So now we can actually go through the process of trying to factor these down and see if we can get this actual answer. So let's see if we can actually see how many actual zeros we have. So if I take a look at this right now, there's not much I can do with this, but I do notice I've got an x cubed, an x squared, and a single x here. So I can pull out one of those x's, and I'm left with x squared minus 5x plus 6. Now this piece here, we can factor that. That's something that you should be able to factor on this one. So we should be able to factor that down, and let's see if we can set this actually equal to 0 and actually figure out what our actual max zeros are. So I'm going to go through here. Nothing I can do with that x, so that x is just going to sit here. I've got x squared minus 5x plus 6. Well, so because of this, I'm going to factor this down. I need factors of 6 that add to give me a negative 5. Well, my factors of 6 are 1 and 6 and 2 and 3. I need them to add together to give me a negative 5. Well, if they're going to be a negative 5, that means that these numbers here have to all be negative. So if I'm looking at this, then I'm going to say this is going to be x minus 2 and x minus 3. Because 2 times 3 gives me a positive 6, which is good. And negative 2 plus negative 3 gives me a negative 5, which is what's sitting right here. And then I'm going to set this equal to 0. So what I'm going to do now is I'm going to take each one of these and I'm going to factor these. Well, not factor, they're already factored. I'm going to set each of these equal to 0, and I'm going to actually figure out where these cross the x-axis. So I'm going to take that first x and set it equal to 0. and then x minus 2 and set it equal to 0, and x minus 3 and set that equal to 0. Go back to this first one here. There's nothing else to do. That one's done. On this one, I'm going to move that 2 over, and I get x is equal to 2. That one's done. On this one, I got that negative 3. I'm going to move it over, and I get x is equal to 3, and that one's done. So if you notice, our max zeros are going to be 3, and I have 3 different zeros here. So my zeros are when x is equal to 0, 2, and 3. And that is what we are looking for on this, okay? All right, let's try this again. This one's going to be a little bit trickier, okay? So I'm going to look at this one here, and I'm going to say, okay, I want to do the same thing. So first off, my max zeros that I can possibly have is going to be 13, okay? So now I'm going to do the same thing I did with the last one. I'm going to pull out what they have in common. So in this case, it's an x squared. So I'm going to pull out that x squared. And I'm left with x to the 11th minus 6x to the 10th minus 27. Okay. Well, there's nothing else I can really do to this. I know for sure this one over here, I can set this x squared equal to 0, which means when I take the square root of both sides, x is equal to 0. So that's definitely one for sure. But this guy right here, this one's a really hard one to look at. So what we're going to do, we're going to use our handy dandy calculator because we have them. So we want to use them. Okay. So you just simply go in here. Oops. We have x to the 13th minus 6x squared. I'm sorry, not squared, to the 12th. And then minus 27x squared. And then we're going to graph this. Let's see what this looks like. All right. So that looks like it's about all it's going to do. So if you notice, we've got this piece right here. That's that 0 piece. And the way you can figure that out is you go second trace. And we want to look at number 2 here for 0. So we're going to go on a little bit on the left side, and then we're going to go over it and a little bit on the right side. And so if you take a look, it's thinking right now. It's thinking. Oh, it's still thinking. Well, okay. I might have went too far. As we get closer to this, if I just type in 0 here, there's my 0, 0. I must have went too far down and too far away from it. So because I went from 0, 0, if you notice that this is going to be this answer right here, okay? Now this person over here, so now we'll go back and do our zeros again. So let's try this one again. And we're going to, again, go to the left side. Oh, did I pass it? Let's go 5.9. Let's go 6.1. It looks like it's going to be crossing at 6. Yep. So we cross here at 6 as well. Okay. So if you notice that this number right here basically means 0. So consider that as a 0. So we are also going to be crossing at x equals 6. So another one of your factors over here is going to be x equals 6. And this one's from the V of the calculator. Oh, I spelled that wrong, didn't I? Calculator. later. Sorry about that, guys. All right. So these are going to be our zeros when we graph it and take a look at it that we're actually going to be focused on, okay? So even though I could have 13, this one only has 2 that we can visibly see. All right. Let's try the next one. X to the 4th minus x, or 8x squared plus 15. So this one here, you need to notice that there's a pattern here, and you should have learned this in Algebra 2, so we're going to go over this again. Anytime you see a setup like this where the middle term's exponent is half of your highest exponent, you can do this thing called use substitution. All right. And so what you're going to do is you're going to come over here and say, okay, I'm going to let u equal whatever your middle variable is. So in this case, x squared, which means that if I squared u and I also squared, in this case, x squared, I get x to the 4th. Because what we're going to do here is we're going to force a quadratic, because we can do that. So now I have these things over here. So what I'm really looking at is u squared minus 8u plus 15. This is now a quadratic equation, and this is something that you know how to do. So what we want to do is just go ahead and factor this like you normally would a quadratic equation. Factors of 15 that add to give you a negative 8. That would be u minus 3 and u minus 5. But you have to remember that this problem is set up in x's. So once you get down to this piece here, you want to come back to this piece right here. And you want to take your u and put your x squared back into it. So you really are looking at x squared minus 3, x squared minus 5. And we're going to set this equal to 0. Because remember, this tells me right here I can have a max of 4 zeros. So now what I'm going to do is I'm going to take each set of these and set it equal to 0. And I'm going to solve. So I get x squared is equal to 3. When I take the square root of x, I get plus or minus the square root of 3. The 5, the same thing. I get x squared is equal to 5. So when I take the square root of x squared, I get x is equal to plus minus the square root of 5. And these, all 4 of these, are my zeros for this specific problem. Okay? So when you go through these, try to look at some of the past techniques that you've done in the past that you can go through and say, hey, I can apply, in this case, a u substitution and turn this into a quadratic and then use my quadratic properties. I can factor things out that they have in common like you did on this one here, and then use your calculator to find the other ones. Or on this one, you just factored it out and you used a quadratic property together. So you just have to use your prior knowledge to be able to go through these problems and actually be able to solve them. Okay? So now, let's talk about repeating zeros. So what happens is sometimes you're going to wind up with an x minus c squared or to the 3rd or to the 4th power or whatever else. And if this happens, this is called a repeating zero. And it's also known as a multiplicity. So a repeating zero and a multiplicity, they both mean the same exact thing. Okay? So what happens is when you're looking at this, your graph is going to do something specific. When it gets to the x-axis, because it's a 0, so when we're focusing on that 0 and it's on the x-axis, if you have a 0 that turns and touches the x-axis and goes back up, you're looking at an even number for your multiplicity. So what that is saying is this here. You've got a graph that's doing this. And what it does, it comes up and it touches and it goes back and it does something else. This right here, that's that 0. So if it's even, it comes up, it touches, and then it turns. It never crosses the x-axis. It only touches. So you can have something that looks like this, or you can have something that does this right here. Oh, that's really big. But it comes down and it just sits on the x-axis. So if that ever happens, you have an even multiplicity. That means you have like x to the 4th, x to the 2nd, x to the 6th. As long as it's an even number, that's what's happening. If it ever crosses, so again, you've got a graph, something that's happening like this, and you've got a graph that comes through and it does this. At this point right here, since it crossed the x-axis and kept on going, that specific 0 has a multiplicity that's going to be odd. So that's going to basically, when we talk about multiplicity, we're talking about 3, 5, 7, 9, any odd number greater than 1. If you keep looking at this specific graph here, so I have an odd multiplicity here, and then I come over here and I have this 0 that sits over here. It comes down and it sits here. So this 0 is going to be an even multiplicity, and that's okay. You can have things like that. So you can have different multiplicities within a specific problem, and that's absolutely a-okay. So if it's odd, it's going to cross the x-axis, and if it's even, it will turn on the x-axis, but not cross it. So first thing we want to do, we want to state the number of possible real zeros and turning points for this specific equation, and then determine all the real zeros and their multiplicity. So we want to state the possible real zeros. So what we need to look at here is we need to look at your x values only. So I've got one x value here. I have one x value here. And then here, even though it says I have 1, I've got that 3. And so I actually have 3. So I've got 1, 2, 3, 4, 5. So actually I have 5 max zeros. Okay. My turning points is going to be whatever this answer is here, minus 1. So that means I have 5 max zeros and 4 turn points. Okay. So now what we want to do, so we got that piece out of the way. Now what we want to do is we want to determine the real number zeros and their multiplicity. So the nice thing about this one, it's already factored for us. So all we have to do is set each one of these equal to 0. So I've got negative 2x. Oh, let's try that one again. So I've got negative 2x, and that's going to be equal to 0. I've got x minus 4, that's going to be equal to 0. And then I've got 3x minus 1 cubed, and that's also going to be equal to 0. Now, what's nice about this cubed piece here, we actually don't have to write this because we're setting this equal to 0. And if that's the case, all we have to do is just do the inside piece, whatever's here. All right, so now I got this first piece here. I'm going to divide both sides by the negative 2. So I got x is equal to 0. So that's my first one. Moving to this one, I've got that negative 4. I'm going to move it over so I get x is equal to 4. So that one's done. Now that one's done. On this one, I'm going to move that negative 1 over. So I get 3x is equal to 1. Divide by the 3. So I get x is equal to 1/3. So if I take a look here, I've got an exponent of 1. So I have no multiplicity here. I've got here, I have an exponent of 1. So I have no multiplicity here. However, here I've got an exponent of 3. So I've got a multiplicity of 3. So that means that when x is equal to 1/3, the graph will cross the x-axis. And it's going to cross the x-axis because we have an odd multiplicity here. Okay? We are going to cross the x-axis at x is equal to 1/3. And if you want to take a look at that real quick, we can come over here to, again, our handy dandy calculator. Turn it on. Clear that. And we have negative 2x. And I'm just going to type it in exactly as it's written. And then 3x minus 1 to the third. And then I'm going to hit graph. Okay. I'm going to type that in right. Yep. And so there is your graph right there. All right. All right. State the number of possible real zeros and turning points for this one, and then determine all the real zeros and their multiplicity. So I'm going to give you a few moments to go through this, and I want you to do everything that's asking you here, and then we'll meet back up and we'll check our answers. So go ahead and pause the video now. All right, welcome back. So let's see how you did. So first thing, my real zeros should be 4. My turn points should be 3. Now, I'm going to take this piece here. I'm going to factor it. I noticed that they all have an x squared in common. So I'm actually going to pull out a negative x squared because I want to change these signs. Because I don't like my lead term to be negative. So I'm going to go ahead and change those signs. That means everybody's going to get a sign change. So now I have that. And then I'm going to factor this piece here. So factors of 2 that subtract to give me a positive 1. So that's x plus 2, x minus 1. And then I'm going to take each one of these and set them equal to 0. So I got negative x squared is equal to 0. I have an x plus 2 is equal to 0. And then x minus 1 is equal to 0. So this is just simply x is going to be equal to 0. And I have that exponent. So I've got a multiplicity of 2. This is going to be x, and I'm going to move that 2 over. It's going to be equal to negative 2. And you notice that there is no extra exponent here, so that's just going to be that. And I have this one here. Move that 1 over, and I get that. And again, there's no other exponent other than 1, so it's just going to be that. So on this one, I've got a multiplicity of 2. X is equal to 0. And then I have these other 2 zeros as well. Okay. All right. State the number, so the same type of question. So we're going to try one more time and see how you do. So let's just run through this one together real quick. So I've got my real zeros. That's going to be a 5. My turn points will be a 4. I'm going to factor this piece out. So I have a 3, an 18, and a 27, and an x cubed. So I'm going to pull out a 3x cubed. That leaves me with x squared minus 6x. And then plus 9. Factor this piece. 3x squared. So I have an x minus 3 and an x minus 3. Notice I have 2 of these. So I have 3x squared. And I have 2 sets of these x minus 3s here. So actually that is what I'm looking at. And then I'm going to set each of these equal to 0. So 3x squared is equal to 0. That gives me my x is equal to 0, and I have a multiplicity of 2. And I have an x minus 3 is equal to 0, so x is equal to 3. And again, because of that right there, I have a multiplicity of 2. Okay? So these are my zeros, 0 and 3. However, I have this multiplicity, so that means they're going to turn and touch on 0 and turn and touch on 3, but they will not cross the x-axis on those two numbers. All right. So let's move on to Descartes' rule of signs. This is an actual easy one. So what this does, it gives you information about the number of positive and negative real zeros. So the first thing we're going to do is we're just going to look at the actual polynomial itself and just count. What we're doing is we're looking for sign changes. And so when we just count, what we're looking at is the positive real zeros for this one. So when we look at just f of x, so actual just a problem, what we are looking for is the positive real zeros. Then what we're going to go do is we're going to go in and we're going to input negative x everywhere and take a look to see if we have any sign changes. And if we do, then we'll count those after we put those in there, and those sign changes will be the negative zeros. So I'm going to go back. I don't know how far I have to go back. Is it here? Yeah. So it'd be like this piece right here where you have the plus minus and the plus minus. This means I have 2 positive and 2 negative zeros. And the Descartes rule will help you determine actually what that looks like. When using Descartes' rule of signs, the number of real zeros indicated includes any repeating zeros as well. So it's going to include those as well. So describe the possible real zeros of the following. So we're not actually going to find these. We're just going to describe the real zeros. So we're going to start here. So we're going to look at our positive ones. And all we're going to do is we're just going to count sign changes. So I have a change here. I do not have one here. I have a change here. And I have a change here. So I have 3 positive zeros that I could possibly have. Now I'm going to take this same equation here, except now I'm going to run it for f of negative x. So I get negative 11 negative x to the 4th plus 20, that's negative x to the 3rd, plus 3 negative x squared minus a negative x, and then a plus 10. So now once I clean this up, this is going to keep me with a negative x, 11x to the 4th. This is going to change, so minus 20x to the 3rd. This won't change from up here because it's an even number. So plus 3x squared. This is going to change, so plus x plus 10. And I'm going to count just like what I did here. So I do not have a sign change. I do have a sign change. I do not have a sign change, and I do not have a sign change. So I only have 1. And if you take a look at this, it makes sense because the max number of zeros we can have is going to be 4. And out of that 4, 3 of them could possibly be positive, and the other one's going to be a negative one. So this is what we're looking for when we're generating our zeros. We know that we can have up to 4, and out of the 4 in this case here, because we have those sign changes, 3 of them are going to be positive, 1's going to be negative. So let's try it again. So we're going to look at our zeros as is. So our positives, so we're just going to read it off how it is. I have a sign change. I have a sign change. I do not have a sign change. So I had two sign changes here. Replace all the x's with a negative x. and then simplify it so you can see if you have any more sign changes. So when I clean that up, I get 3x to the third, and I get a plus 2x squared plus x minus 1. So no sign change, no sign change, one sign change. So my negative, that gives me one sign change. And again, that makes sense because I have my max number of zeros possible is going to be 3. Okay, take a moment, pause the video, tell me how many positives and how many negatives you're going to possibly have. Ready, go. All right, welcome back. So, positive. Nope. Oop, try that again. Nope. Yep. And nope. So for my H, and I plug in a negative in here, I get negative 6x to the fifth plus 8x squared plus 11x minus 15. So yep, nope, and yep. So my negatives is going to be 2. Okay. So again, now notice that these numbers don't have to add up. That's okay. They don't have to add up to that. But just be aware, the max that you can have is going to be that number. All right. That means that we have a multiplicity hiding in here is all that means. All right. Last part, rational zero theorem. Now, again, this is something that you should have remembered from Algebra 2. So with the rational zero theorem, this describes the leading coefficient and the constant term of the polynomial with integer coefficients that can be used to determine a list. So this is what we're doing. We're generating a list of all possible rational zeros. Now, this list can be extremely long, and that's okay. All those answers are not going to be the actual answers. All this is doing is just generating a list of numbers for us to look at. And we can verify these by mainly looking at the calculator to actually see where they cross the x-axis or touch the x-axis, okay? So that's what we're going to be looking for when we're doing this. All we're doing is going to generate a list, and the rational zero theorem is going to teach us how to do that. So if you're given a polynomial and the lead term of the coefficient is 1, then any rational zeros of that polynomial of the integer are just the factors of the constant term. So all these here have a coefficient of 1. So I don't have to do anything separate. So when I look at these, I'm only going to be focusing on this last number here, okay? So when I get to this one, I only need the factors of that one because there's a 1 sitting here that you don't see. So for this one, my only options for my rational list, so this is your rational zero list. And these are only a possible thing. It's always going to be plus minus. And in this case, the factors of 1 is just going to be 1. Okay. For this one, my list. So I'm going to take the factors of 9. Remember, everything is going to be a plus minus. So I've got 1 times 9 and 3 times 3. So I've got plus minus 1, plus minus 3, plus minus 9. And you're done. So this is just generating that list. On this one right here, I'm only going to focus on this one. So my list is my factors of 30, which is 1 and 30, 2 and 15, 3 and 10, 5 and 6. So I've got plus minus 1, plus minus 2, plus minus 3, plus minus, oops, plus minus 5, plus minus 6, plus minus 10, plus minus 15, and I'm going to end with a plus minus of 30. All right, so that is when you have a coefficient here of 1. Now, if you have a polynomial and your lead coefficient is anything other than 1, you have a little bit more work to do. And so what you're going to do is you're going to find all the factors of that lead coefficient. So we're going to call that term Q. Then you're going to find all the factors of the constant, which is what you just did. We're going to call that P. And then what we're going to do is we're literally going to divide P by Q. And don't forget, all your answers are in the plus minus format. So, for instance, if I gave you f of x is equal to 2x squared plus 5x minus, let's go 7, okay? This is my P, this is my Q. So my factors for P, in this case, is 1 and 7. Remember, everything is plus minus. My factors for Q are 1 and 2. So I'm literally going to take my p-values and divide them by q. So I get plus minus 1 divided by 1, plus minus 1 divided by 2, plus minus 7 divided by 1, and plus minus 7 divided by 2. And this is my list. Okay? It's P divided by Q. And you're just taking those factors and doing it. Let's try one more. F of x is equal to 3x to the third plus 6x squared minus 5x plus, let's go 12. That's got some pretty good numbers to it. So our P, so this is our P. 1, 2, 3, 4, 6, and 12. Our Q is simply 1 and 3. So that means when we generate our list, our P divided by Q, we're going to start with this one. Go 1 over 1, 1 over 3. Oops. And then go to the next number. 2 over 1, 2 over 3. Go to the next number. 3 over 1. Now, when I go 3 over 3, I get 1. So since I get 1, I've already got that represented here. I don't need to do that again. So I'm done with that. Go to the 4. 4 over 1, 4 over 3. 6. 6 over 1. Now, again, 6 over 3 is 2. I have 2 represented right here, so I don't need to worry about that. I'm going to go to 12. That's 12 over 1. And then 12 over 3 is 4. I have that represented there. So again, I don't have to worry about that. Okay. So this is my list of possible zeros I could possibly have. All right. That brings us to the end of zeros of polynomials. So go into Delta Math, do your practice problems in there, check Google Classroom to see what problems you're going to be working on out of your textbook. Make sure you're sending me reminds and emailing me, and I will see y'all in class. Have a great day, guys. TTFN. Ta-ta for now.